Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. You begin to notice it only after looking closely. Across every corner of physics, a quiet rhythm repeats itself. Stones in the air, planets in orbit, light drifting through glass, everything moves as if one hidden instruction guides it all. Scientists working in completely different fields keep finding the same underlying rule. It appears in classical motion, in quantum behavior, and in the geometry of spacetime. Wherever we measure, one principle seems to whisper the shape of every path nature takes. Tonight, you wander into that principle gently. How a single idea can predict trajectories, light travel, particle interactions, and the deep structure behind the laws of physics themselves. One question rises slowly out of that realization. Why does one unseen rule seem to steer everything? Across history, observers noticed something subtle. Motion somehow prefers elegance. A planet arcs around its star with grace, a photon slips through transparent material, an electron circles a nucleus with perfect balance. Different systems, different scales, yet the same behavior keeps returning, as though nature always chooses the smoothest way forward. Scientists eventually named this idea the principle of least action, though the rule existed long before equations or textbooks. It favors the path that minimizes effort, time, or imbalance, even in systems that have no intention, no awareness, no mind. In this calm journey, you trace that rule through experiments, measurements, and discoveries from NASA, ESA, JWST, Chandra, Gaia, LIGO, and observatories around the world, watching how a single principle touches every part of physics. Centuries ago, long before satellites or lasers, Pierre de Fermat studied how light bends between air and water. No one knew why angles changed the way they did. But Fermat noticed something astonishing. Light always bends in exactly the way that makes its travel time minimal. It never takes the slower route. That realization opened a door. Mathematicians like Euler and Maupertuis began to see that nature seemed to prefer certain curves, trajectories, and motions. They called the quantity involved action, though they didn't yet understand its purpose. They only knew that nature behaved as if it made this action stationary. Everything deepened when Joseph Louis Lagrange entered the picture. He developed a new language for motion, not one based on forces, but on energy. He defined a quantity called the Lagrangian, the difference between kinetic and potential energy. Integrate it over time, and you find the action. And when you look for the path that makes this action stationary, Newton's laws appear naturally, without being assumed or invented. It is as if the universe had only one instruction all along, and all of Newton's rules were simply shadows of it. Picture a simple throw. You release a ball, and it rises, slows, and falls back in a perfect, soft arc. We explain it using gravity and velocity, but there is another viewpoint. Among countless possible paths, only one makes the action stationary. That is the path nature selects. This same principle guides spacecraft today. NASA planned the journeys of Voyager 1 and Voyager 2 using optimization methods tied to action-based mechanics. Cassini's months-long maneuvers around Saturn followed paths so close to stationary action that the spacecraft required only gentle course adjustments. It was as if the probes were gliding along routes nature had already shaped. Light obeys the same rule. Modern experiments send laser beams through glass and measure their angles with exquisite precision. Every single result confirms Fermat's insight. Light always behaves as if it chooses the quickest passage. Then came Richard Feynman, who carried this idea into the quantum world. He imagined a particle not selecting one route, but trying every possible route between 2 points. Every zigzag, every curve. Most of those paths cancel out through interference, leaving only a narrow family of paths around the stationary action. Suddenly, quantum mysteries became clear. Interference patterns, tunneling, atomic spectra, measurements from Chandra, results replicated in labs around the world. All of them aligned once expressed through action. In our time, the principle stretches even further. The ESA Gaia mission has mapped more than 1 billion stars with accuracy down to tiny fractions of an arc second. Those maps reveal that stellar motions across the Milky Way follow paths exactly predicted by least action mechanics. Stars take the curves that spacetime and energy naturally favor. Not because they know, but because the structure of reality offers them no other choice. Gravity itself obeys this rule. Einstein's general relativity arises from minimizing the Einstein-Hilbert action, a single expression from which the curvature of spacetime unfolds. It predicts how light bends near massive bodies, how stars orbit black holes, how time slows near dense mass, and how gravitational waves ripple through the cosmos. When LIGO recorded gravitational waves in 2015, the waveform matched predictions derived from stationary action with breathtaking accuracy. Even space itself seems to flow along nature's preferred paths. Across every age of physics, the same pattern appears. Lasers in a laboratory, rockets drifting between planets, galaxies spinning far beyond sight. The universe arranges motion as if optimizing quietly, not with intention, but simply as a consequence of its geometry. And now, a gentle next step begins to form. If matter and motion obey stationary action, then light, bending, traveling, and arriving with uncanny precision, becomes one of the clearest ways to see this principle at work. You begin to wonder, how does a photon, racing blindly through air, water, vacuum, or gravity, always arrive along the path that takes the least time? There is a moment in physics that feels like magic when you truly see it. A beam of light behaves as though it knows the fastest way before it travels it, not approximately but exactly. Through glass, mirrors, warm and cool layers of air, or curved spacetime, light follows the path that extremizes travel time. Careful experiments with lasers and atomic clocks only deepen this mystery. And as you sit with that realization, your thoughts soften, like ripples fading on a quiet surface, guiding you gently toward rest. The more precisely scientists measure light with spacecraft and telescopes, the more clearly a quiet pattern reveals itself. In this part of our journey, you drift deeper into that mystery, following a simple question in optics that slowly grew into a pillar of modern physics. You travel through experiments, history, and the quiet moments when someone simply watching a beam of light realized there was something deeper hiding inside its path. It begins before we had a name for photons or a language for waves. In the 1600s, Pierre de Fermat wondered why light bends when it passes from air into water. No one knew how fast light traveled in any material, but by watching those bending angles, Fermat noticed something almost impossible to ignore. Light always seems to find the quickest way between 2 points, even if that means curving or changing direction. This insight became known as Fermat's principle of least time. Fermat didn't know why light behaved this way, but his idea made predictions so precise that centuries later, with the most sensitive optical instruments humans have ever built, we still find his principle exactly correct. Every reflection, every refraction, every tiny bending of a beam follows his rule. To sense the beauty of this, picture a beam of light passing from air into glass. If it traveled straight, it would move slowly inside the glass, where light speed is reduced. If it dipped too sharply, it would travel farther than necessary. Among countless potential paths, one route strikes the perfect balance between speed and distance, and that is the path light always takes. But Fermat's idea was only the first step. 2 centuries later, James Clerk Maxwell united electricity and magnetism, revealing that light is an electromagnetic wave. Yet, even inside this new framework, when Maxwell's equations were rewritten using action principles, the same quiet pattern appeared. Light follows the path that makes the action stationary. Fermat's minimum time rule and the deeper principle of least action turned out to be 2 descriptions of the same hidden structure. Everything changed in the 20th century when science finally built instruments capable of watching light with microscopic precision. Laser interferometers measured timing differences between beams traveling along different routes. High-speed detectors tracked bending angles down to tiny fractions of a degree. NASA tested laser communication between spacecraft and Earth, and once again, the data matched Fermat's predictions almost perfectly. Every measurement whispered the same truth. Light behaves as if all possible paths are tested, and only the path with stationary action remains. To see this more clearly, imagine a beam striking a mirror at a slight tilt. Part of the light reflects upward, part downward. Yet every reflection follows one exact rule: the angle in equals the angle out. This is not a random geometric trick. It is the single angle that makes travel time stationary. Any other reflection angle would take longer. Light simply follows the optimal route without calculation or effort. Across laboratories, researchers place transparent blocks on rotating platforms and send narrow lasers through them. As the blocks rotate, the refracted beam sweeps across screens. Every point it lands is exactly where least time predictions say it should be. These experiments, repeated thousands of times under different conditions, tell the same story. Light adjusts automatically, always maintaining stationary action. Then physics stepped into the quantum world, and the mystery deepened. In the 1940s, Richard Feynman proposed something astonishing. A photon doesn't begin by choosing a single path. It tries every possible path, straight, curved, winding, unpredictable, from source to destination. Each path carries a phase, and when all paths interfere, most cancel out. Only a small cluster near the stationary action survives, forming the single route we observe in everyday reality. This is how quantum behavior reduces to least action, not by intuition, but through interference, waves, and mathematics. Quantum experiments confirmed this beautifully. In double-slit experiments, photons fired one by one create interference patterns that match path integral predictions. Signals moving through optical fibers for thousands of kilometers behave in precise agreement with least time rules. Even the bending of light across galaxies follows the same logic. The James Webb Space Telescope has captured arcs and rings, distant galaxies stretched by gravity into luminous curves. These shapes match stationary action calculations exactly, even after billions of years of travel. Light still follows nature's optimal route. Behind every discovery, there is a quiet moment of realization. When Hubble first observed gravitational lensing in the 1990s, astronomers were amazed by how closely the bending matched Einstein's predictions. But deep beneath Einstein's equations lies a single truth: those predictions come from minimizing the action of spacetime itself. Those enormous natural telescopes, made from galaxy clusters, are not just cosmic curiosities. They are direct experiments on the largest possible scales, showing that light follows stationary action everywhere. As technology improved, the consistency only sharpened. Laser ranging experiments, bouncing signals off mirrors left on the moon, measure the Earth-Moon distance to within millimeters. These results confirm light's behavior to more than 8 decimal places. Any deviation from least time predictions would be obvious immediately. None has ever been detected. Even today, as JWST studies ancient light stretched by cosmic expansion, every observation supports the same idea. Dark matter halos, invisible yet traced by their influence on light, distort paths exactly the way stationary action requires. The universe behaves like a vast, invisible lens, and light travels through it with the same rule it has followed since the first galaxies formed. This raises a gentle curiosity inside you. If light always finds the path that extremizes travel time, and if this behavior mirrors stationary action in every branch of physics, then perhaps the rule guiding light is not unique at all. Maybe it is simply another expression of the deeper principle shaping motion everywhere. As we continue, a new pattern begins to settle into place. Newton's familiar forces fade from view, replaced by a cleaner, quieter framework where motion follows the structure of an action rather than any direct push or pull. Part 3 begins. Why can Newton's complicated forces be replaced by one simple action? There is a moment in physics that can feel almost unreal. You realize that the forces Isaac Newton described, ideas that transformed science forever, might not be the deepest layer of reality. The pushes and pulls we learn as children, the arrows drawn on diagrams, the equations describing motion, all of them soften when you look closely enough. And beneath them lies something smaller, calmer, and easier to state, a single quantity called the Lagrangian. If you allow a system to move in a way that makes its action stationary, Newton's forces appear automatically, not as separate laws but as natural consequences of one principle. The complexity of motion becomes the surface texture of something simpler underneath. From here, our focus shifts to that deeper structure. You explore how Newtonian mechanics slowly transformed into a description based on action rather than forces. And you follow the experiments and history that reveal why this shift became one of the most important transitions in all of physics. The story begins with Newton, 3 centuries ago. His laws let humanity describe falling apples, circling moons, spinning wheels, and wandering comets. 4 generations, Newton's 3 rules looked complete, final. But as time passed, scientists noticed something subtle. Newton's formulation was powerful, but messy. Every situation demanded identifying each force: gravity, tension, friction, pressure, springs, one by one. The deeper researchers went, the more tangled the work became. Then came Joseph Louis Lagrange. With quiet clarity, he asked a different question. Could motion be described by energy rather than force? He defined the Lagrangian, kinetic energy minus potential energy, and found something astonishing. If you choose the path that makes the action, the time-integrated Lagrangian, stationary, Newton's laws emerge naturally. No forces required. It wasn't philosophy. It worked. Every experiment Newton explained through pushes and pulls could be recovered simply by minimizing action. You may imagine a falling stone, but instead of thinking about invisible hands pulling on it, you picture something quieter, a path drawn across an energy landscape. In the older way of thinking, gravity forces the stone downward and sets its speed. In the newer view, the stone simply follows the route that balances motion and potential in just the right proportion so that the action is perfectly still. That path, the one nature always chooses, matches the same graceful curve Newton described, but it springs from a different foundation. The motion is not pushed. It flows. Scientists soon began to notice a curious pattern. Using Lagrange's method was not just another translation of Newton's ideas, it made tangled problems suddenly simple. A spinning top, a rolling wheel, a swinging rope in a quiet laboratory. Systems that once filled pages with force diagrams could now be understood in a few clean lines built only from energy. And then, everything shifted. This quiet shift from forces to action did more than make calculations easier. It became a bridge. Electromagnetism, optics, quantum physics, even the structure of spacetime itself began to fall naturally into place when viewed through this deeper idea. Newton's forces, brilliant as they were, could never unify all these areas. The Lagrangian could. The evidence hides in places both familiar and extraordinary. Every modern space mission depends on action principles. NASA navigates spacecraft using methods rooted in least action because they offer unmatched precision. The delicate glide of Cassini through Saturn's moons, the elegant gravity assists used by Voyager, and the perfectly timed maneuvers that allowed Mars orbiters to slip into place, all of these depend on calculations that mirror nature's own preference for optimal paths. A single mistake in these predictions could send a spacecraft drifting thousands of kilometers off target. Yet they arrive exactly where they should, because the universe itself follows these rules. As the 20th century unfolded, the Lagrangian became far more than a clever mathematical tool. It turned into the foundation of theories that described the world at its most fundamental levels. Maxwell's electromagnetism was rewritten in terms of an action, making electricity and magnetism two faces of a single phenomenon. Quantum field theory was constructed by writing Lagrangians for every particle and interaction. The Standard Model, confirmed in experiments at CERN, Fermilab, and laboratories across the world, is nothing more than a carefully built Lagrangian written in symbols, each term describing a piece of reality. Even Einstein's description of gravity falls out of an action, the Einstein-Hilbert action, not from forces at all, but from the quiet geometry of spacetime. Behind every major discovery lies this same quiet idea. When physicists announced the detection of the Higgs boson in 2012, they were not simply celebrating a particle. They were confirming that the structure of the Lagrangian they had trusted for decades was correct. That structure describes how fields give mass to particles, how motion and interaction weave together. Every tiny signal, each peak in the data, every statistic matched the predictions of a Lagrangian crafted long before the experiment. Astronomy offers its own confirmations. The Gaia mission has mapped more than 1 billion stars with astonishing precision. Their movements, slow rotations, spirals, oscillations, complex orbits, match predictions built from least action mechanics. Newton's forces can describe these motions, but least action shows why they emerge in the first place. In the ripples of spacetime, the connection becomes clearer still. When the LIGO observatory first detected gravitational waves from merging black holes, scientists compared the signals to simulations based on Einstein's equations. Those equations come directly from minimizing an action written into the geometry of spacetime itself. The match was breathtaking. Frequency, amplitude, and the rising chirp of two distant black holes spiraling together aligned with predictions to astonishing precision. Even spacetime follows the rule of stationary action. So why does any of this matter? Because replacing the language of forces with the language of action reveals something profound. Instead of a universe governed by many separate rules, everything begins to look like consequences of one underlying principle, that nature chooses paths where the action is still. Newton's familiar equation, force equals mass times acceleration, becomes not a fundamental command, but something that emerges naturally when we apply the Lagrangian to simple systems. It is a surface pattern arising from deeper geometry. When scientists push further, the picture becomes stranger and more beautiful. Particles no longer look like tiny objects obeying pushes and pulls. They start to behave like ripples exploring every route space allows. In this deeper layer, the stationary action principle does something remarkable. It becomes the link between the smooth motion we see in everyday life and the quantum world underneath. And that takes us to one of the most astonishing questions physics has ever asked. Do particles really explore every possible path before arriving where we see them? You can see this connection between the quantum world and everyday motion most clearly in experiments that reveal interference at surprising scales. In 2013, scientists guided large molecules, each made of more than 100 atoms, through thin diffraction gratings. To nearly everyone's astonishment, the resulting patterns still showed interference. More complicated, yes, but unmistakably quantum. Even large objects, far bigger than electrons, obey the same path integral rules. The only reason we don't notice this in daily life is that, for large objects, most possible paths cancel so completely that only the stationary action route remains visible. This idea appears again in particle accelerators. When electrons and protons are pushed to nearly light speed inside circular tunnels at CERN or Fermilab, their behavior lines up perfectly with predictions made from action-based quantum field theories. Countless paths contribute behind the scenes, yet the measured results, collision energies, scattering angles, and the patterns written in detectors reflect the interference of all possible histories, reduced to the final outcome we observe. Even in astronomy, the path integral approach leaves delicate fingerprints. Photons traveling across billions of years pass through regions filled with ordinary and dark matter. Their paths bend and stretch, producing gravitational lensing. The arcs and rings captured by the James Webb Space Telescope, distant galaxies smeared into graceful curves behind massive clusters, match predictions drawn from quantum electrodynamics woven together with general relativity. Those predictions assume photons explore many possible routes through warped spacetime, with the stationary action path emerging as the one we see. The deep field images recorded by JWST become a cosmic scale confirmation of the same principle. Behind every major step in quantum thought lies a journey from confusion toward clarity. In the 1920s, early quantum researchers argued over how electrons moved. Some imagined neat, planetary orbits. Others envisioned smooth waves filling space. The picture changed when Richard Feynman united both views with the sum over histories approach. Once you assume that every particle explores every path, and that interference selects the outcome, the strange consistency of quantum experiments becomes natural. This approach does not erase Einstein's doubts about quantum mechanics, but it explains why predictions work with unmatched precision. When physicists test quantum electrodynamics, theory and measurement agree to within 1 part in a trillion, one of the most precise agreements ever achieved in science. Such accuracy is only possible because the path integral method includes every subtle contribution to a particle's behavior. In modern physics, the idea reaches far beyond electrons and light. If gravitons, hypothetical carriers of gravity, exist, they too would follow path integrals. Strings in string theory vibrate according to action principles that include every possible shape the string might explore. Even attempts at quantum gravity often begin by extending Feynman's ideas to curved spacetime. Again and again, the same principle returns, hinting that reality at its core may be shaped from interference, probabilities, and action. With this foundation, a new direction opens. A shift where fields begin to take center stage. If particles trace paths through a landscape of possibilities, then perhaps the fields creating those particles reveal something deeper within the framework itself. Part 5. How can one equation describe both fields and the particles inside them? There is a quiet moment in modern physics when a familiar idea suddenly feels unfamiliar. The moment you realize that the universe is not built from solid particles at all, but from fields, and that every electron, every photon, every ripple of the Higgs is simply a vibration in one of those fields, shaped entirely by nature's tendency to minimize its energetic cost across spacetime. One equation, the Lagrangian of the Standard Model, contains every one of them. Every mass, every charge, every spin. It feels almost unreal the first time you hear it. Most of us grow up imagining particles as tiny beads with definite edges and permanent shapes. But when researchers examined matter closely using bubble chambers in the mid-20th century, and then giant detectors at CERN decades later, the data painted a different picture. Reality did not point to solid objects. It pointed to ripples, disturbances, brief excitations in invisible fields that fill all of space. Particles are not separate things moving through a backdrop of fields. Particles are the fields, localized, quantized, temporary waves. This idea formed slowly. In the 1920s and 1930s, scientists struggled to merge quantum mechanics with relativity. Their equations were unstable or inconsistent. But something changed when they wrote the problem in terms of a Lagrangian. By letting a field minimize its action, the mathematics suddenly behaved. From that point, a single coherent structure emerged: quantum field theory. Instead of patchwork rules for particles, physics shifted to a unified framework where fields evolve by minimizing action throughout spacetime. A simple example makes it clear. Consider the electron. In school, we picture it as a point. Yet in high-energy experiments at CERN or SLAC, electrons show no internal structure at all. They behave like stable vibrations in an electron field. Wherever that field oscillates in a certain way, we say an electron is present. Its charge, its spin, its mass, these are not attachments. They are consequences of how the field lowers its action. The electron becomes the most efficient vibration allowed by the universe's Lagrangian. This insight transformed particle physics. Every particle became a note played on a hidden instrument, the underlying field. Photons are ripples in the electromagnetic field. Quarks are ripples in quark fields. Gluons are ripples in the strong force field that binds quarks together. Even neutrinos, ghost-like travelers that pass through your body by the trillions every second, are ripples in neutrino fields spread everywhere through space. One of the deepest examples is the discovery of the Higgs field. For decades, physicists noticed that the Standard Model seemed right, but it required one missing explanation: where mass comes from. Why does the electron have mass while the photon does not? Why do different quarks weigh different amounts? The Lagrangian predicted consistent masses only if a new field permeated all of spacetime, a field whose lowest action state was not zero, but a constant background value filling everything. This was the Higgs field. A particle's mass would depend on how strongly it interacted with this field, how difficult it was for its vibration to travel through the Higgs background. For nearly 50 years, this remained a prediction. Then, in 2012, in the Large Hadron Collider at CERN, the ATLAS and CMS experiments detected a new boson, the long-awaited ripple of the Higgs field. A tiny bump in a graph drawn from trillions of collisions confirmed it. Mass was not built into matter. It was a consequence of the energetic cost of disturbing the Higgs field. The Lagrangian structure, long trusted, was correct. Evidence appears everywhere. Cosmic rays raining through Earth's atmosphere match predictions from quantum field theory. X-ray spectra recorded by NASA's Chandra Observatory align perfectly with field calculations. In condensed matter labs, quasi-particles behave as emergent field vibrations. And across billions of light years, the spectral lines in light captured by the James Webb Space Telescope match the same rules. Atoms forming soon after the Big Bang obey the same Lagrangian as atoms forming today. At the center of quantum field theory lies an elegant unity. The same action principle that guided planets and photons earlier in our journey also governs fields. Across scales, the universe minimizes action, and the Lagrangian becomes the underlying script from which every motion is written. Differences among particles arise not from separate laws, but from how their fields interact with the Higgs. A photon crosses the Higgs field effortlessly and has no mass. An electron interacts more strongly and becomes heavier. A top quark interacts intensely, resulting in enormous mass. The Lagrangian does not assign mass like a label. Mass appears as a natural outcome. Even spin, a quantum property with no everyday analog, emerges from the structure of a field. Its symmetry, its orientation, its allowed transformations in space. Behind these ideas lies a history of quiet brilliance. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg proposed a unified electroweak theory using a Lagrangian that assumed broken symmetry. Their predictions, including the W and Z bosons, were confirmed at CERN in the 1980s. Every success reinforced the idea that the Lagrangian approach was not simply elegant but true. Evidence keeps gathering. Neutrino oscillations in giant underground detectors in Japan. Measurements of muon magnetic moments at Fermilab. High-energy collisions in the LHC. Atoms captured by telescopes in distant galaxies. Again and again, nature matches the Lagrangian's predictions. As this picture settles into place, a new question rises from the mathematics. What if electricity and magnetism, once separate ideas, also emerge from one principle? Part 6. Why do Maxwell's equations fall naturally from a single action? One of the quiet revelations in physics is that the entire structure of electromagnetism, electric fields, magnetic fields, visible light, radio waves, X-rays, can arise from a single action, not from a bundle of independent laws. Maxwell's equations, famous and elegant, become not separate statements but consequences of requiring the electromagnetic field to minimize its action. This insight changed the direction of theoretical physics. It meant electromagnetism was unified not by analogy or experiment alone, but by structure. To see why this matters, we begin with something simple. Electricity and magnetism were once separate topics. In the early 1800s, electricity flowed through wires. Magnetism came from iron stones. No single idea connected them. Then, in 1820, Hans Christian noted something quiet but unusual. A wire carrying electric current could sway a magnetic needle. A modest finding, yet it revealed a hidden connection waiting to be explored. Over the next decades, Michael Faraday followed that thread with patience. In 1831, he demonstrated that when a magnetic field changes, it can produce an electric current. He arranged coils, spun magnets, and ran his experiments again and again. He realized that the strength of the effect depended on how quickly the magnetic surroundings shifted. Faraday relied on observation and intuition rather than equations, but what he uncovered created the outline that James Clerk Maxwell would later express in precise mathematics. Maxwell began gathering these discoveries in the 1850s. When his work was complete, he produced a set of equations describing how electric and magnetic fields develop, influence one another, and travel through space. Those equations pointed to something no one had directly witnessed. Electric and magnetic fields could sustain each other while moving, forming waves that travel at a constant rate. Maxwell calculated that speed and recognized it instantly. It matched the known speed of light, about 299,792 kilometers per second. For the first time, light had a physical explanation. It was an electromagnetic wave. Even this alone would have secured Maxwell's place among the most important physicists in history. But something deeper was still hidden inside those equations. The mathematics was correct, but it appeared complicated. 4 separate equations in 3-dimensional space filled with curls, divergences, and cross-terms. Powerful, elegant, and useful, but not yet merged into a single idea. That unity would come later, when physicists began relying on the principle of action as the foundation for describing the laws of nature. In classical mechanics, the action principle already explained how things move. In quantum theory, it described how particles interfere with one another. Researchers wondered whether fields could be treated the same way. They could. And when scientists wrote the action for the electromagnetic field, one integral describing how the field behaves in space and time, and then required that this action be stationary, all of Maxwell's equations emerged naturally. No extra assumptions, no separate ingredients. Everything flowed from a single action. This result is now a central part of theoretical physics. The electromagnetic action is constructed from the field strength, a quantity that measures how the electromagnetic field varies across space and time. When that action is minimized, it generates the equations that determine electric and magnetic behavior. This explains how electromagnetic waves travel. This explains the reliable motion of radio signals. This explains why X-rays act consistently, whether in a testing chamber or in distant clusters of galaxies. All of these behaviors are encoded in one action. The strength of this idea becomes clear when you compare it with real observations. Think of the Van Allen radiation belts surrounding Earth. First found during NASA's Explorer 1 mission in 1958, these belts hold charged particles captured by Earth's magnetic field. Their form, rotation, and interactions are direct results of Maxwell's equations. The shape of the belts, ring-like regions circling the planet, comes from the geometry of magnetic field lines described by the same action that governs every electromagnetic field. Now consider the solar wind, a continuous stream of charged particles flowing from the Sun spacecraft such as NASA's Parker Solar Probe and ESA's Solar Orbiter have detected how the solar wind responds to the Sun's magnetic field. These measurements reveal spirals, oscillations, waves, and magnetic flips that behave exactly as predicted when Maxwell's equations are derived from electromagnetic action. Even instruments designed to capture light from the early universe depend on these principles. JWST's NIRCam and MIRI instruments rely on the predictable behavior of photons, tiny pieces of the electromagnetic field, to determine the elements and distances of ancient galaxies. When JWST records the redshift of faraway galaxies, it is measuring how electromagnetic waves stretch as space expands. The ability to read that stretching comes directly from knowing how light moves according to Maxwell's equations. Every branch of astrophysics, radio astronomy, infrared surveys, optical observations, ultraviolet studies, X-ray science, gamma-ray observations, relies on the same structure. The Chandra X-ray Observatory collects high-energy radiation from neutron stars and black holes, radiation created in rapidly changing electromagnetic fields under intense gravity. ALMA studies cold gas and dust using radio waves described by the same action. Even Earth-bound radio telescope networks, like those used by the Event Horizon Telescope to image the black hole in M87, depend on models of how electromagnetic waves travel through interstellar material. The essential insight is that all of these observations come from one action. There are no separate rules for radio waves, no separate rules for visible light, no separate rules for gamma rays. All are solutions to the same equations derived from the same action. This unity makes electromagnetism one of the most successful theories in all of science. It explains phenomena ranging from household electronics to quasars releasing energy billions of light years away. In laboratories, synchrotrons speed up electrons close to the speed of light, producing X-rays whose spectrum match the predictions based on Maxwell's equations. In medicine, MRI systems rely on changes in magnetic fields, again governed by the same action, to image tissues with remarkable clarity. One of the most impressive qualities of electromagnetic action is its stability across scales. A radio wave several kilometers long follows the same rules as a gamma ray created when neutron stars collide. The magnetic field inside a small laboratory coil follows the same principles as Jupiter's massive magnetic environment measured by NASA's Juno spacecraft. This universality reflects the strength of building physics from action. It ensures that behaviors remain consistent in every environment where electromagnetic fields exist. The path by which physicists recognized this unity includes many key moments. In the early 20th century, special relativity showed how electric and magnetic fields transform when viewed from different perspectives. What once seemed separate became parts of one electromagnetic structure. Later, quantum electrodynamics, the quantum version of Maxwell's theory, produced predictions that match experiments to 12 decimal places. No other scientific theory has reached such accuracy. All of this arises from the same classical action. When extended into quantum theory, it continues to describe nature with extraordinary power. Today, the electromagnetic action is written using four-dimensional spacetime, which naturally includes both electric and magnetic components. This four-dimensional view fits with Einstein's relativity. When physicists express the action in this form, the resulting equations automatically respect spacetime symmetry. This is another reason the theory works so well. It aligns with the geometry governing gravity. Because of this, electromagnetism blends smoothly into larger theories. It fits inside the Standard Model as the electromagnetic half of the electroweak force. It interacts with quantum fields in reliable ways. It allows atoms to bond, molecules to exist, and stars to emit light. In every case, the same action provides the foundation. As the structure of electromagnetism settles, another step appears. A shift that moves from fields to the geometry that contains them. Because if electromagnetism comes from minimizing its action, and gravity comes from minimizing the Einstein-Hilbert action, then both rest on the same underlying rule, even though they show themselves in very different forms. This connection prepares the ground for the next question. Part 7. How does gravity become geometry? When you minimize action in spacetime, you reach a quiet transition in physics, a moment when gravity stops appearing as a force at all. A moment that can feel surprising, because everything you thought you understood about falling apples, orbiting planets, and drifting galaxies begins to change. Look closely, and gravity reveals no push, no pull, no invisible force stretching across space. Instead, it becomes something softer, something woven into the shape of spacetime itself. A geometry that objects move through naturally, simply by taking the path of least action. And once you realize this, it becomes impossible to unsee. The fall of an apple, the curve of a thrown stone, the slow turning of stars around the center of the Milky Way, all are geodesics, the smoothest possible paths through a flexible spacetime. Not because anything drags them, but because the universe's geometry directs their motion. At this point in the journey, you turn toward the idea itself, looking at the measurements, the early confirmations, and the long sequence of observations that recast gravity as shape rather than force. A shift that began long before gravitational waves were detected and long before astronomers traced stellar motion in the hearts of galaxies. Motion across the Milky Way. The earliest clues surfaced in the late 1800s when Albert Einstein began questioning Newton's picture of gravity. Newton treated gravity as an instant force acting across space, drawing objects together no matter how far apart they were. This model worked beautifully for centuries, until astronomers found slight anomalies in Mercury's orbit. No matter how carefully the gravitational pull of the Sun and neighboring planets was calculated, Mercury followed a path Newton's equations could not perfectly match. Something small was missing, subtle but persistent. Einstein suspected the issue was not with the planets, or the Sun, or any invisible force, but with spacetime itself. What if spacetime wasn't an unmoving backdrop, but a flexible structure shaped by energy and mass? What if objects simply moved along the straightest possible routes available within this curved geometry? That idea settled gradually, eventually forming what Einstein called the general theory of relativity. At the center of this theory lies the Einstein-Hilbert action, a quantity that describes how spacetime curvature behaves. Minimizing this action produces Einstein's field equations. These equations do not describe forces. They describe how matter shapes spacetime, and how spacetime guides matter. Put simply, gravity moves from being a force to being geometry. To understand how elegant this is, imagine dropping a ball in Newton's framework. Gravity pulls it downward. In Einstein's framework, the ball just follows the straightest line through curved spacetime, a geodesic. Much like a bead sliding on a curved wire, nothing pushes or pulls it. It only follows the shape available. The falling ball does the same thing, but its path is inscribed in spacetime itself. This idea may seem abstract until you compare it with real observations. In the 20th century, astronomers measured the bending of starlight passing near the sun during a solar eclipse. The light curved by exactly the amount predicted by general relativity, not Newton's laws. Nothing was yanking on the light, it simply followed spacetime's curvature. Decades later, NASA's gravity probe carried ultra-precise gyroscopes into orbit. Those gyroscopes drifted slowly over time, not because of mechanical flaws, but because Earth's rotation drags spacetime around with it, a phenomenon known as frame dragging. General relativity predicted the precise amount of drift. Newtonian gravity could not. Once again, gravity revealed itself as geometry. The same story appears on galactic scales. ESA's Gaia mission mapped positions and motions for over 1 billion stars. Astronomers modeled those motions using geodesics of curved spacetime. The predictions matched reality with dazzling accuracy, showing how stars move through the geometry carved by visible matter, dark matter, and everything between. Even the shapes of galaxies turn into geometric evidence. JWST deep field images display rings and arcs, the signatures of gravitational lensing, where light from distant galaxies becomes distorted by massive clusters along its path. The curves match geodesics calculated from Einstein's equations down to astonishing precision. The clusters do not pull the light, they reshape the spacetime the light travels through. Nothing more. Nature repeats this behavior everywhere. Then came the most dramatic proof of all. In 2015, the LIGO detectors in the United States sensed tiny ripples passing through Earth, gravitational waves created by 2 black holes merging more than 1 billion light-years away. The chirping signal, a rising tone that traced the spiraling collapse of the black holes, matched general relativity with breathtaking detail. This was not a force radiating through space. It was spacetime itself stretching and compressing. The exact waveform emerged from minimizing the Einstein-Hilbert action across an extreme, dynamic geometry. Behind this milestone lies decades of effort. Engineers built 4-kilometer vacuum tunnels, isolating mirrors sensitive enough to detect changes smaller than 1,000th the width of a proton. Einstein doubted these waves would ever be observed. Yet the moment they were detected, the signature of spacetime curvature was unmistakable. Nothing in that measurement made sense if gravity were a force. Everything made sense if gravity were geometry. This geometric nature also clarifies black hole behavior. Inside a black hole, curvature is so intense that even light cannot escape. Around black holes, spacetime twists and spirals, effects captured through the motions of hot gas and warped starlight by NASA's Chandra X-ray Observatory, Hubble, and JWST. The orbits of stars near Sagittarius A*, the black hole at the center of the Milky Way, follow geodesics that match Einstein's predictions with incredible precision. ESO's gravity instrument measures those orbits to within tens of micro-arcsecons, showing spacetime bending tightly around the black hole. Every measurement, from star clusters to gravitational waves to the slow precession of Mercury, points to the same conclusion. Gravity is the shape of spacetime, not a force living inside it. And the tool that reveals the shape is the same principle we've traced from the beginning. The stationary action principle. The Einstein-Hilbert action encodes spacetime curvature. When minimized, it produces Einstein's equations. Those equations generate geodesics. And those geodesics describe every orbit, every fall, every cosmic motion. With gravity understood as geometry, a new question begins to form. One where the action principles governing fields and spacetime begin hinting at a broader framework researchers have chased for nearly a century. Because if curved spacetime emerges from minimizing its action, naturally we must ask, What happens when that curved spacetime meets the quantum fields that operate inside it? Part 8. Why does the same principle shape both quantum fields and curved spacetime? There is a moment in modern physics that feels like stepping into a hidden doorway. A realization that two of the most powerful ideas ever built, quantum field theory and general relativity, rest on a shared foundation. Different equations, different scales, different domains, yet both guided by one rule. The universe evolves by making its action stationary. Once seen, this connection cannot be unseen. Quantum fields, which describe particles as ripples in invisible structures spread across space, emerge from actions written in their Lagrangians. Spacetime, in Einstein's theory, curves according to the Einstein-Hilbert action. Fields obey stationary action. Geometry obeys stationary action. Two pillars of physics, one rule beneath them. Here we begin exploring that connection with care, following the evidence and theoretical paths that led scientists to suspect these two seemingly separate areas may be different faces of one deeper structure operating below them both. The story starts in the early 20th century, when researchers struggled to understand the quantum world. Electrons acted like particles and waves simultaneously. Photons interfered with themselves even when fired individually. Atoms emitted spectral patterns too precise to ignore. To explain these results, physicists began treating particles not as tiny objects, but as excitations of fields spread everywhere. Those fields evolved according to actions. Minimizing those actions produced equations that matched experiments perfectly. Quantum electrodynamics, quantum chromodynamics, the Higgs mechanism, each emerged by writing a Lagrangian, computing its action, and finding the states that made that action stationary. This technique became the backbone of the Standard Model, the framework describing every known particle except gravity. It predicted quarks, gluons, and weak bosons long before detection. And when CERN discovered the Higgs boson in 2012, that success confirmed not just one particle, but the entire Lagrangian structure beneath quantum fields. Meanwhile, gravity was telling its own story. Einstein's theory framed gravity not as a force but as curvature. Matter shapes spacetime. Spacetime directs matter. This picture came from minimizing the Einstein-Hilbert action, which encodes how curvature responds to mass and energy. Vary the action, and Einstein's equations appear. The mathematics is so elegant, it feels almost inevitable once action is chosen as the foundation. Two theories, two mathematical worlds. Yet both follow the same guiding rule: nature takes the path of stationary action. As physicists recognized this parallel, a quiet question formed. If quantum fields and spacetime geometry both obey action principles, could a deeper action exist, one that unifies them? The search for such a master action began almost immediately. In the mid-20th century, physicist John Wheeler argued that information underlies everything, famously summarizing his view with "it from bit." He guessed that particles, fields, and spacetime geometry might come from some deeper informational structure, something beneath both theories. In the decades that followed, efforts to build a theory of quantum gravity explored this idea from multiple directions. String theory proposed that particles are not points, but tiny vibrating strings. Each vibration becomes a different particle. These strings evolve according to an action, the Nambu, go-to action, which controls how they move and oscillate in spacetime. When the math is carried out, gravity appears naturally as one of the vibration modes. The result stunned researchers in the 1970s. In this picture, gravity is not an added feature, it is built into the action defining the string. Loop quantum gravity took an entirely different route. Rather than treating particles as strings, it proposed spacetime is woven from tiny loops, discrete bits of area and volume. These loops also evolve according to action principles. Their shapes, linkages, and transformations form the geometry Einstein described, but now at the smallest possible scales. If spacetime has a granular structure, loop approaches attempt to derive that structure by minimizing action across the network. These models differ in details, yet share a quest for a single action explaining both quantum fields and curved spacetime. Though no single theory has achieved unanimous acceptance, each reveals new connections. Observational data supports the idea that the quantum and gravitational realms share a common foundation. Consider gravitational waves. Spacetime ripples were first detected by LIGO in 2015, faint waves arriving from deep in the cosmos. Their forms matched general relativity's predictions with uncanny accuracy. Yet the energy they carry behaves in a way that feels almost quantum. These waves overlap, combine, and travel with patterns reminiscent of wave functions. No one has seen a single graviton yet, but the mathematics suggests gravitational waves behave as collective vibrations of a deeper field, similar to how photons arise in electromagnetism. Again and again, nature presents a bridge between worlds that once seemed separate. You can see this pattern in the ancient light surrounding us. The cosmic microwave background, mapped by satellites like COBE, WMAP, and Planck, holds tiny temperature variations imprinted during inflation. Those small imprints began as quantum fluctuations, then stretched to cosmic scale. Over billions of years, they guided the formation of galaxies, clusters, and the long filaments of matter threading through space. What started as minute ripples in quantum fields eventually became gravitational landscapes millions of light-years across. This evolution only makes sense if both realms follow compatible principles shaped by action. Black hole physics gives another glimpse. Hawking radiation, the faint emission of particles near a black hole, arises when quantum fields interact with extreme curvature. NASA's Chandra Observatory and ESA's XMM Newton have observed X-ray behavior consistent with these processes, matching quantum field theory predictions in curved spacetime. This area, often called QFT in curved spacetime, works because both gravity and quantum fields emerge from actions that determine their behavior. The alignment is subtle, but unmistakable. And in 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. Its glowing ring, its thickness, its brightness, all of it matched simulations based on Einstein's equations combined with quantum models of plasma near the horizon. Two separate theories, one describing geometry and one describing fields, functioning together with precision. Not by coincidence, but because each is shaped by minimizing an action. Across the universe, the same quiet rhythm returns. Whether scientists measure the bending of distant galaxies, collisions of particles moving near light speed, or ancient radiation from the Big Bang, they see evidence that quantum fields and curved spacetime belong to a single conversation. They feel like two chapters of the same story, written in different styles, yet guided by the same underlying rule. All of this leads to a slow, persistent question. If quantum fields and gravitational curvature both follow action principles with the same kind of structure, could they be two approximations of a deeper action we have not yet found? String theory, loop quantum gravity, causal sets, emergent spacetime, holographic dualities, each tries to reveal that deeper action. Each attempts to show that information and geometry might be two sides of one reality. None has provided a final answer, but the search continues because the pattern is too clear to ignore. And as these ideas settle, another possibility begins to appear. One where the constants of nature no longer look like separate numbers, but like parameters set by the Lagrangian of the universe. In this view, the masses of particles, the strengths of interactions, and the structure of atoms arise from the same rule shaping spacetime and fields. Part 9. Are the constants of nature simply tuning settings in a cosmic Lagrangian? There is a moment in physics that feels almost surreal. The moment you realize that the numbers you once memorized, values scattered through textbooks like isolated facts, might actually be adjustable settings in a single mathematical description. A set of instructions the universe has followed since its first instant. Particle masses, force strengths, angles inside nuclei, they look random on paper. But inside the Lagrangian, the action that governs reality, they behave like carefully chosen weights shaping everything we observe. Now the idea unfolds slowly. Instead of seeing constants as disconnected measurements, you begin to see them as parts of a shared pattern. They seem to set the stage for atoms, stars, chemical bonds, and the stable environments needed for complexity to emerge. It begins with a simple inventory. the mass of the electron, the charge of the proton, the strength of electromagnetism, the ratio between weak and strong forces. Dozens of values measured with incredible precision. They work perfectly in experiments worldwide, yet none can explain why they have those exact values. The standard model treats them as inputs, numbers you must supply before the equations can run. But once these values sit inside the standard model Lagrangian, their behavior changes. They stop appearing random. They become precise weights balanced with extraordinary care. Raise the electron mass slightly and chemistry breaks apart. Alter the strong nuclear force a little and atomic nuclei fail to form. Adjust the Higgs field's constant background and atoms lose stability. These are not philosophical speculations. They are calculations tested by decades of experiments. Measurements at CERN, neutrino observations in Japan's Super Kamiokande, atomic spectra observed by NASA's Chandra, and the patterns in the cosmic microwave background mapped by ESA's Planck satellite. All agree on one delicate set of values. Physicists call this fine-tuning. Many constants must lie within narrow ranges or the universe becomes unrecognizable. If the strong nuclear force were slightly stronger, almost all hydrogen would fuse in the early universe, leaving no water or stars like the Sun. If it were weaker, nuclear binding would fail. Either way, reality would unfold differently. The balance begins to look structured rather than accidental. To understand why the Lagrangian matters, step back and see how modern physics describes nature. Every particle, electron, quark, neutrino, boson, arises from a field. Each field has a Lagrangian. Every term in the Lagrangian carries a constant, a number that sets the energetic cost of changing that field in spacetime. When the universe minimizes its action, these numbers determine everything. A mass becomes the cost of vibrating a field. A charge becomes the cost of interacting through electromagnetism. Mixing angles determine how quarks transform in stars and in particle accelerators. Nothing is random. Everything is encoded. The Higgs field offers a clear example. Its discovery at CERN in 2012 confirmed predictions made decades before. Particle masses are set by their coupling to the Higgs background, a value maintained since the universe cooled after the Big Bang. Shift that value, and electrons become too heavy or too light. Atoms fail to form. Stars burn too fast or never ignite. Planets cannot keep atmospheres. Electromagnetism reveals a similar precision. The fine structure constant, about 1/137, sets how strongly electrons bind to nuclei. Change it slightly, and the periodic table collapses. Elements heavier than helium would never exist. Images from JWST contain galaxies filled with carbon, oxygen, nitrogen, elements formed in stars and scattered through space. Those elements exist only because this constant allows stable atoms to form. Even the cosmic microwave background adds evidence. Planck mapped tiny temperature variations in the early universe, patterns shaped by force strengths. Alter them, and cosmic expansion becomes too fast or too slow for galaxies to grow. The ripples match predictions using the same constants found in particle physics. Two very different fields, cosmology and quantum theory, shaped by the same numbers. All of this hints at a deeper idea. The constants of nature may not be arbitrary. They might be settings in a single cosmic Lagrangian, coefficients in the action that describes reality. Change the action, and the universe changes. Space-time curves differently, quantum fields vibrate differently, atoms behave in unfamiliar ways, and stars live shorter lives or never form. Decades of work support this vision. In the 1960s, experiments at Brookhaven suggested quark mixing, showing that mixing angles influence particle transformations. Later, scientists at CERN measured those values with tremendous accuracy. In the 1990s, Super Kamiokande discovered neutrino oscillations, requiring new parameters in the Lagrangian. With every discovery, one pattern persisted. Constants must lie within narrow ranges or physics fails. Astronomy tells the same story. JWST sees early galaxies forming stars through reactions predicted by nuclear physics. These reactions depend on proton masses, neutron masses, weak force strength, and strong force binding. If those constants shifted, the light from ancient galaxies would look completely different. Some physicists wonder whether the universe chose these constants in its earliest moments, not by purpose, but by the structure of the action guiding spacetime and fields. In this view, fine-tuning simply reflects the universe settling into the Lagrangian that yields the lowest action, the configuration that allows stable particles, atoms, and stars. Carl Sagan once said, "We are a way for the cosmos to know itself." But long before consciousness emerged, the cosmos needed constants that allowed complexity. The Lagrangian might be the script that made it possible. Across all of physics, the coherence is striking. From colliders to telescopes, from stellar evolution to quantum mechanics, the constants behave like coordinated settings in one mathematical structure. As scientists explore dark matter, dark energy, and quantum gravity, many suspect the Standard Model is only a small section of a larger framework, waiting just beyond reach. From here, another step approaches. If the constants behave like settings in a deeper Lagrangian, the next question is what happens when we extend that logic to its limit, when the action of the universe determines everything, from galaxies expanding to spacetime itself. Part 10. If a single principle explains all of physics, what does that say about reality? There is an idea so quiet yet so powerful that once seen, it reshapes the universe. Instead of dozens of independent laws, everything begins to look like a single instruction, whispered through spacetime since the beginning. Not a memorized rule, not a single equation, but a principle so deeply rooted that black holes and quantum particles follow it without exception. The universe evolves by extremizing its action. Every moment in this journey has led toward that understanding. Light bending through glass. Electrons choosing paths of stationary interference. Fields adjusting their vibrations. Planets following geodesics through curved spacetime. Each phenomenon, no matter how different, echoes the same hidden structure. Action minimized, motion chosen, history written. Tonight, you let the structure of reality open like a quiet book. You look across fields and particles, across shapes, constants, and the long history of the cosmos. Not to solve anything, but simply to notice how everything begins to feel connected when it grows from a single, silent idea. To see how far that connection reaches, you start with something almost ordinary, a simple falling object. Newton described its motion as a pull, an invisible force drawing it downward. But Einstein offered a gentler picture. The object takes the most natural route through spacetime, a curve shaped by mass and geometry. When physicists place Einstein's equations inside the Einstein-Hilbert action and look for the path that minimizes it, the motion appears on its own. The action guides the shape. The geometry adjusts. The object just continues, without anything pushing or tugging. Then you move from a falling stone to a wandering beam of light. A photon never accelerates or slows, yet its path bends. Not because something acts on it, but because the route of least action in a curved spacetime is no longer straight. During eclipses, NASA measured starlight shifted ever so slightly, exactly as the Einstein-Hilbert action predicted. Different size, different setting, the same quiet rule. Now step into the quantum world, where the shapes become stranger. An electron does not follow one path. It considers every possible path, and the ones with nearly stationary action reinforce one another, while the rest fade away. Feynman described reality as a sum of histories, each weighted by action. Every interference pattern, every probability wave, every test in quantum mechanics reflects this idea. Quantum fields are not invented. They are shaped by the action that defines them. When scientists organized the Standard Model, its collection of particles did not appear as separate pieces, but as ripples in fields guided by a single action. Masses, force strengths, mixing behaviors inside atomic matter. All come from coefficients in that action. When CERN found the Higgs boson in 2012, it confirmed that every particle's mass is tied to how strongly it interacts with the Higgs field, resting at the minimum of its own action. Whether a particle is heavy or light, stable or short-lived, strong or delicate, every property is determined by how the action measures disturbances in its fields. This is not theory for its own sake. It is tracked by detectors, recorded in accelerators, seen in synchrotron radiation, and confirmed by decades of measurements. And then your view stretches outward, far beyond laboratories, to the universe as a whole. The cosmic microwave background, mapped by Kobe, WMAP, and Planck, holds faint ripples that began as tiny quantum fluctuations in the first moments of time. As the universe expanded, those ripples stretched, later becoming galaxies, clusters, and long filaments of structure reaching hundreds of millions of light-years. The same action that shapes subatomic fields planted the seeds of cosmic structure. Two extremes, one principle tying them together. When the James Webb Space Telescope examines ancient galaxies, the chemical lines in their light reveal nuclear processes rooted in the Standard Model action. When ESA's Gaia mission traces the movement of more than 1 billion stars, those paths follow geodesics made by minimizing the action of spacetime. When LIGO hears gravitational waves, the signal lines match solutions to the Einstein-Hilbert action for merging black holes. None of these discoveries came from guessing. They all began with the same approach: write an action, minimize it, let reality reveal its path. This raises a quiet and lingering question, one that has guided research for decades. If quantum fields and curved spacetime both arise from stationary action, could they come from a single, deeper action we have not yet identified? For nearly a century, this idea has driven attempts at quantum gravity. In string theory, particles appear as vibrations of tiny extended objects, each following a string action. In loop quantum gravity, spacetime might be built from discrete loops governed by a quantum action of their own. Holographic models, causal set theories, emergent spacetime ideas, all suggest that information and geometry could share a single origin. None of these frameworks are complete, yet all reflect the same intuition: the unity is too consistent to ignore. Even black holes point to this connection. Hawking radiation comes from quantum fields near curved geometry. The information paradox, a question explored for generations, hints that neither quantum mechanics nor relativity alone can explain the deepest regions of spacetime. Somewhere beneath both, a single action must exist, shaping quantum fluctuations at the edges and curvature at the center. Science has passed through moments like this before. Electricity and magnetism once seemed unrelated, before Maxwell joined them. The weak and electromagnetic forces appeared separate, until they merged into the electro-weak interaction. Today, many physicists suspect that quantum fields and gravity may be the next pair waiting to be joined, not by stitching equations together, but by discovering the single action from which both naturally arise. If such an action is ever found, reality would no longer look like a collection of different laws. It would appear as one continuous structure. Every field would be a small shift in that structure. Every particle, a ripple. Every geodesic, a natural line through its shape. Every constant of nature, a single parameter within a deeper pattern. Every cosmic event, another step in its unfolding. That thought brings you to a soft final place. Not an answer, but a direction. Because if every part of existence, from the smallest tremor in the vacuum to the largest clusters of galaxies, follows the principle of stationary action, then somewhere beyond what we understand, the universe may be expressing one quiet mathematical form. A form we are still learning to read, piece by piece, discovery by discovery, night after night. Resting in that possibility, the long line of scientific history begins to feel connected. From Newton's falling apple to the ripples in spacetime recorded by LIGO. From quantum interference to the glow of ancient galaxies seen by JWST. From the Higgs field giving particles their mass to the cosmic web stretched across billions of light-years, every part of the universe behaves as if guided by one gentle instruction woven through existence. And now, as this final thought settles in your mind, the journey reaches a quiet pause. Not a conclusion, but a moment to breathe. Because many patterns remain in darkness, waiting for tomorrow's questions. If this exploration offered calm before sleep, I'm grateful to have shared it with you. May the night be deep, peaceful, and full of rest, until curiosity returns for the next journey.